Okay, so we had just derived an expression for the escape velocity from planet Earth, but I'd like to put this to another use, this result we got, and calculate some other stuff, but stay a little closer to Earth. I want to talk about the International Space Station. I want to ask two questions. How fast are you going around the Earth at the International Space Station, and how much time is there between breakfasts at the International Space Station? In other words, what's the length of a day? And the day should be defined as the time from sunrise to sunrise, just the way we do it down on Earth here. So it turns out you have to know something about the International Space Station. And a few years ago, we actually got to talk here at Cornell with a Cornell alumnus named Ed Lu, and he had a chat with us as he flew overhead. Now, when he flew overhead, which, by the way, he was carrying along Ezra's Cornell socks, and we'll have to look into the archives to figure out how that all came about. But he literally went over our heads, and we had 11 minutes of radio contact with him over at Barton Hall using the amateur radio station, and a crack team of radio operators that kept the antenna on target and took care of something called the Doppler shift, which you'll hear about later on that in the course, and that's next semester. And what happens is it was a wonderful conversation. And actually, you might not believe it, but it's true that when Ed went over our heads, he was actually closer to us physically as the crow, well, if the crow could fly up into space, than if the crow were to fly to New York City. So we're talking only a few hundred miles, a couple hundred miles or so over our heads. That's because the atmosphere around the Earth is very, very thin, okay? And by the way, I can't help but bring up a fantastic illustration that shows you what an awesome guy Newton was in terms of thinking. In Newton's Principia Mathematica, where he explained mechanics, revealed it to the world, he imagined a situation where he was heaving projectiles, not up, but sideways. And he did a physics 101 type thinking, and he said, look, suppose there's a mountain here, and I shoot out a cannon and I fire it off. He knew that if you did it close by, it would follow a nice arc and land down there. And at this time, you're so close that you didn't even imagine that the Earth was anything but flat. You know, it's a pretty good approximation when you're a short distance in there. So he just did that kind of calculation we know about. Then he imagined, suppose you shoot out that cannonball with more velocity. And by the way, he's neglecting air friction here. Tall mountaintop, right? So what's going on is you shoot this thing even further out, and she falls to the Earth a further distance there. But suppose you gave it so much muzzle velocity that something kind of risky for the cannoneers occurs. You shot it out, and it went right around the old Earth like that. No air friction here, and whoop! There it is. Look out behind you. Here comes that cannonball. That was what Newton thought about. And it was a beautiful idea because you're always kind of falling at the Earth, but you ended up going all the way around there. He got the idea of an orbit like that. And it's precisely the thing to think about. Now, again, I want to emphasize how thin the atmosphere is. And that's an amazing thing when you think of air pollution. There's such a tiny distance compared to the radius of the Earth, which, remember, was about 4,000 miles, and we're just talking a couple hundred miles here. This is all you've got to get above the Earth's surface and to avoid any air friction for the International Space Station is just to get up a couple hundred miles, and that's what NASA did. So we can now answer the question of how fast you're going around in the orbit because we know all about centripetal forces, okay? So centripetal forces says the following thing. It says, if you want to balance the force, get the right force of gravity that will match what you have to do this kind of orbit, forget about that altitude. Just call your distance from the center of the Earth, which is what you get to think about these kinds of problems. As long as you're on the outside, you can just think about the center of the Earth and the force of gravity. Then you're going to have the mass of the International Space Station, mass of I, times little g. Okay, that's downwards, and that has to match your centripetal force, which has to be down, it's downward there. In this case, it's going to be mass of the International Space Station times v squared of the International Space Station as it whips around the Earth at the distance out there of r, the radius of the Earth, because again, we ignore the height. So that's acute relation. Let me simplify and say, we now know that we can solve for that speed that we want, speed squared. It's going to be given by g, little g times r, okay? And unsquare that thing, so we get an expression, vi equals the square root of g times r. Well, guess what? In our earlier video, when we needed to go to get the escape velocity, it turned out that that we're almost there. It's just off by a factor of square root of 2. So if we take this result, which said earlier, we found out that this thing happens to be 11.2 kilometers per second, and just divide this by that result by the square root of 2, that tells me that this is going to be equal to that. When I punch it out on my calculator there, it's going to end up being about 7.9 kilometers per second. That's your velocity, kilometers per second, or in miles per second. It's not that high a speed, it's lower, of course, because you're dividing by the square root of 2, 5.0 miles per second. So the International Space Station is actually whipping around the Earth at a high speed. It takes the Earth a whole 24 hours to rotate, over 2 pi times r, 2,500 miles, 25,000 miles there. And so what's going on is you're covering a lot of distance. Well, I wanted to know how long between breakfasts on the International Space Station. How long does Ed have to wait before he can have another breakfast up there? And the answer is surprising here. When you take the speed that we're talking about, which we now have right down here, remember it's about 8 kilometers per second or 5 miles per second, and just convert that into a period of a day, one time around. That says take the, what do we need to do here? We've got to take the distance you're going to cover, all right? We can say t day up there is going to be 2 pi r of the Earth, the radius of the Earth, let me say it this way, that this is the velocity of an orbit, all right? So the velocity of the International Space Station, or speed of the International Space Station, is this in 1 day. Okay, so now I have an expression. Just say t of a day up there is equal to 2 pi of r divided by the velocity that we just figured out down here, the velocity in orbit of the International Space Station. And when you pump in those numbers, again, we remember last time we looked this up, this is 6.4 kilometers altogether. 1,000 kilometers, 6.4 thousand kilometers. And well, just to write it out here, 2 pi, 6.4 kilometers times 10 to the 3 kilometers is the distance there, divided by this number here, 7.9 kilometers per second. And when you do that, you end up with about 5,000 seconds. And that's going to end up, divide that by 3,600 seconds in an hour, and that amounts to 1.4 hours, okay? All right? So Ed gets to eat a lot of breakfasts up there. He gets to have a breakfast every about 1.5 hours, when we have to wait a whole 24 hours. So isn't that a great thing?